Vibrations are in oscillatory motion about an equilibrium position. The oscillatory motion can be defined in terms of its displacement, velocity, or accelerations, with all three of these parameters depending on the excitation frequency. The higher the frequency of excitation, the larger the acceleration of the motion. Within a structural system will be a series of natural frequencies. These are problematic frequencies which produce constructive responses between the structure and the vibrations. The natural frequency depends on the system's stiffness and mass distribution, with each natural frequency having a unique deflection shape or mode associated with it. Structures can respond to excitations in several different ways. Tonal excitation, which is resonant, tonal excitation, which is forced, or broadband excitation. A resonant tonal excitation is when a discrete excitation frequency matches with a natural frequency of the system, allowing the excitation to drive the natural frequency of the system in resonance. A forced tonal excitation is when a discrete excitation frequency does not match with the natural frequency of the system. Thus, the system is vibrated at a much lower levels than the resonant case. Lastly, there is broadband excitation. This is when the vibrations excite a range of frequencies. Generally, the response levels are lower than the purely resonant vibrations due to the energy of excitation being spread over a wide frequency range. Vibrations can cause dynamic stresses, which, if above a critical level, can result in the initiation and propagation of fatigue cracks. Fatigue life of components in response to vibrations varies depending on the dynamic stresses, excitation frequency, and nature of the vibrations. They can, in the end, be very short. Welds are often the most sensitive locations when it comes to fatigue, and vibrations can also cause fretting issues, where fretting is the wearing away of surfaces in contact due to cyclic movement.